chapter 7 basically, and that'll be it for today. No lab, which is good because Melissa couldn't make it today. She's here remotely.
Oh yeah, I was like, you said she was here. I was like, where?
She's on Zoom. So we were talking about absorption spectroscopy. Where absorption is when light is absorbed, causing a transition from some ground state to some excited state. And that can be a change in electronic levels, vibrations, rotations, or translation. Power is the energy of a beam that reaches a given area per second. Intensity is power per unit solid angle. These are related to amplitude squared for the wave. We have Beer's law, which is that amplitude equals epsilon BC. The amount of light absorbed by a sample is dependent on the path length, the concentration of the sample, and a proportional and transmittance is power over initial power. Absorbance is minus log base 10 of transmittance. So if transmittance is 100%, absorbance is 0. If transmittance is 0%, absorbance is infinity. And notice that these are flipped here. Now, for Beer's law, absorbance is epsilon BC, which means, of course, that A1 over A2 equals B1 C1 over B2 C2. And so the path length, B is the cell distance in centimeters, the concentration is the sample concentration in moles per liter. So you can get information on the concentration with an identified epsilon and lambda. And it doesn't hold at high concentrations, and absorbance is much greater than 1. So here's an example. If a solution was 3.78 times 10 to the minus 3 molar in X, and it had a transmittance of 0.212 when measured in a 2 centimeter cell, what concentration of X would be required for the transmittance to be increased by a factor of 3 to 0.636 when a 2 centimeter cell was used? So for this, I'll go through this. I actually worked this out. Our initial transmittance is 0.212. Our initial concentration is 3.78 times 10 to the minus 3. Our initial cell length is 2 centimeters. We want to find concentration 2 when transmittance is 3 times as much. Transmittance 2 is 3 times T1, so it's going to be 0.636. Absorbance is epsilon BC, which means absorbance over BC is epsilon. And that means absorbance 1 over B1, C1, and absorbance 2 over B, C2. In this case, B is the same in both cases because the cells are the same size. They're both 2 centimeters. So absorbance 1 over C1 equals absorbance 2 over C2. The concentration 2 is going to be concentration 1 times absorbance 2 over absorbance 1. Well, we have the transmittances, so now we need to turn them into absorbances. Absorbance is minus log of T. So absorbance 1 is going to be minus log of T1. So minus log of 0.212 gives you 0.674. and minus log of 0.636 gives you 0.197. And that's a typo. I mean, it's an obvious typo, but I should fix it. So concentration 2 equals concentration 1 times absorbance 2 over absorbance 1. I'll re-upload these slides. I'll try to remember to do it by next week. So concentration 2 is going to be 3.78 times 10 to the minus 3 molar times absorbance 2, which is 0.197 over absorbance 1, which is 0.674, which comes out to 1.1 times 10 to the minus 3 molar. And I just refreshed my memory on the test. There will be questions on the test about going from absorbance to transmittance and vice versa. And there'll be questions on the test about using absorbance to find concentration, but I'm not going to have a combined one like this one. So this is actually a little more complicated than even the test will have. So let's talk about the components of various instruments. We have the basic design for some UV visible absorbance measurement or some measurement device. We have a source, we have an entrance slit, we have a device that disperses the light into various colors, which could be a prism or a diffraction grating. We have a sample, and then we have a detector. So you have a light source, you have a wavelength selector, which is the the entrance slit. That's this part. You have the sample cell holder, and then you have the detector. And then there's an amplifier and a recorder hooked up to that. So just in general, for a spectroscopic instrument, you have a light source, you have a wavelength selector of some sort. The general term for that is a monochromator. Then you have a sample and a light detector. So the components, you have some sort of stable radiation source, you have a wavelength isolation, you have a transparent sample holder and optics, a detector, and then signal processing. So we'll talk about some common components for various instruments. And we're going to go into detail when we look at each type of measurement, what common stuff is. So properties you want for your things. For light source, you'd like to have a stable light source. So your P0 is constant. The output power of your light source doesn't change significantly over time. And it has good precision. You'd also like it to be intense, as bright as possible. Therefore, it's easier to see changes in absorbance. It's easier to see how much gets absorbed. So more intense is useful. Your wavelength selector, you have sort of two contrasting goals. You'd like to have a very narrow band pass. You'd like to very precisely choose the wavelength you want. But you also want to let a lot of light through to increase your input power. But this is a trade-off. Generally, ways that let you select nicely your wavelength will decrease your power, because it's generally done by making slits thinner. So you're literally letting less light through. So that's a trade-off. That's one of the big trade-offs you have to take into account. The band pass, because just in general, a narrower band pass corresponds to less light passing through, which means less input power. Your sample cell holder, you want to have a fixed geometry. you want to have constant cell length because your absorbance depends on how long your cell is. So you'd really like your cell to always not change in size. This is also why in spectroscopy, cells tend to be square or rectangular. Because with a round cell, if you're a little bit off center, you can have a significant change in the cell length. But with a square cell, if you're a little bit off side to side, it doesn't really change things. And you want to make sure that your sample cell transmits the wavelengths of interest. It would be bad if your cell absorbed what you were trying to observe. So for certain things, if you'd like to see shorter wavelengths, you can't use a plastic cell. You have to use like a quartz cell because quartz is transparent up to shorter wavelengths, higher energy. Well, plastic will absorb it. But plastic cells are cheaper. So if you don't need those shorter wavelengths, use the plastic cell because they're cheaper and less of a pain to work with. I mean, including quartz cells. They're reusable, but the plastic cells are a lot easier to work with in many ways. And then your detector. You want it to be a nice stable detector and sensitive to what you're looking at. So you use different detectors for different ranges of wavelengths and frequency. So light sources for UV visible. Some possible options are things like deuterium and hydrogen lamps. This is in the UV range. This is short wavelength. It's a continuous source with a broad range of frequencies. It's based on the electric excitation of hydrogen and deuterium at low pressure. You have a filament and an electrode. You form an electric arc. It's like an arc lamp. And a sealed quartz tube that has some deuterium or hydrogen in it. So in the presence of the arc, some of the electrical energy gets absorbed by the deuterium or the hydrogen, which results in the dissociation of the gas and the release of light. And it's sort of a fuzzy, broad spectrum sort of release. So that's one common source. This is for shorter wavelengths if you want UV light. So it's bright at the shorter wavelength. The energy varies continuously from about 160 nanometers up to 375 nanometers in the UV range. These are different frequencies going into D prime and D double prime. Your cell needs to be made from quartz because glass will absorb light at wavelengths less than 350 nanometers. And they're expensive. They cost like $350 to $500 for the light bulb. So here's an intensity spectrum for the deuterium out of lamp. You can see it drops off a lot and it gets funky down at the visible. Most common, tungsten filament lamp. It's like a classic light bulb. It's a continuous source with a broad range of frequencies. It's based on black body radiation, which is well understood. It has a nice consistent wide range of wavelengths. You heat a solid filament up to glowing. The light emitted will be characteristic of the temperature more than the nature of the filament. It's a tungsten filament because tungsten has a really high melting temperature. We have a low pressure bulb with a tungsten filament. You get the tungsten filament nice and hot and emit light across the whole UV visible spectrum. It goes from the visible into the near IR. It's not so great in the UV usually. There's a little bit less in the UV, but this is the most common light source in UV visible instruments. They're relatively inexpensive. They're straightforward and well understood. Typical tungsten lamp has a temperature of around 2,870 Kelvin with a wavelength range from like 350 to 2,500 nanometers. That's, the cutoff there is where glass cuts you off, basically. You need high temperatures to get high light intensity and low wavelengths. So the higher the temperature, the lower the wavelengths you get out of it. But they're cheap. The wavelength mass is inversely proportional to the temperature, and they cost $10 to $15. Also, if you run them hotter, they don't run as long. The rate of decay is also proportional to the temperature you run them at. There are also xenon arc lamps, which are a continuous source with a broad range of frequencies from 250 to 600 nanometers. They work by passage of current through xenon that causes thermal excitation. This causes blackbody emission. This gives very intense radiation over the frequency range. It was developed for searchlights during World War II. The problems are that I have higher heat, more stray light, higher cost, and shorter lifetimes. And they're kind of a little pricey. So depends on what you're trying to do. You can use a xenon lamp, a hydrogen and deuterium lamp, a tungsten lamp, and then if you want to do visible down into IR, the Nernst glower. For IR stuff, you tend to use things like a nichrome wire or a glow bar as a source. And there are also things, these are line sources, which just output in a single wavelength. So a line source is when you want to look at a very specific wavelength. You could use a laser or a hollow cathode lamp. And you might use that when you have a known wavelength you're interested in, but there's also some other things. Lasers are often used for calibrating. So an FTIR system has a laser in it. The laser is used to calibrate the interferometer. Basically, you can look at how this known wavelength changes as the interferometer moves and use that to figure out how much you've actually moved. Now, your wavelength selection, you can use a variety of tools. For very short wavelength UV, with vacuum UV, you can use a fluoride prism. For most of the UV, you can use a fused silica or quartz prism. For visible and UV, visible and near IR. For near IR, you can use a glass prism. For IR, you can use things like salt prism, NaCl prism. Or for far IR, you might use a potassium bromide prism. But more often, you get things like gratings, which can cover, the whole range depending on how finely spaced the lines are on the grating. So you choose the spacing of the lines based on what wavelengths you're interested in. So if you're interested in short wavelengths, you might do something like 3,000 lines per millimeter. Longer wavelengths is 50 lines per millimeter. There are also interference wedges which can be used. Those tend to be from visible down into IR, or various interference filters are discontinuous. It's just a filter, but it's based on interference. It pulls out just certain wavelengths. And then various filters, like colored filters, basically. So wavelength selectors, a monochromator is some tool that separates out specific frequencies from polychromatic light. It only allows certain wavelengths to be selected and used. The most common sorts of monochromators are dispersing monochromators, and there's two main types. You can have a prism monochromator, where you have your light source goes through a prism. It's separated into various wavelengths because the refraction index varies. So different wavelengths get bent different amounts. That's what happens, when you see a rainbow from a prism. And so there's some dispersion curve where the index of refraction varies with wavelength. And you want to work in areas of normal dispersion for prisms. Because anomalous dispersion occurs generally near where a substance itself absorbs light. And that's not great for your monochromator. So this range, you have some variation, and you use that for purpose. Because Snell's law is index of refraction 1 times sine theta 1 equals index of refraction 2 times sine theta 2. And so no refraction occurs if light is at the normal or if theta 1 equals 0. So the light has to hit a prism at an angle. So the most common is a 60-degree prism like this, where it goes in, bends, and then bends again as it goes out. But sometimes they use half of one with a mirror in the middle. So it goes in, bounces off the back, and comes out, but it still gets dispersed. But you can also have a grating monochromator. A grating monochromator is based on diffraction of light and constructive and destructive interference of that diffracted light. So a transmission grating, which is like these gratings that I showed you, is one where you run the light through it. A bunch of grooves or slits and some transparent material. You get interference patterns. Different wavelengths will have this constructive interference at different points. And you can select the desired wavelength by letting light at different points into the instrument. Basically, you have a movable slit, or generally, I think you rotate the diffraction grating. And so you can have that as a transmission grating. And the nice thing about transmission gratings is that the diffraction gratings, the way they separate light out is nice, tends to be nice and linear, because it's this angle-based relationship where the spacing is based on the wavelength. So they separate wavelengths in a nice linear way. You don't have any curve you have to fit. But also pretty common is to use a reflection grating, which is the most commonly used for monochromators. It's a grooved surface with a reflective coating. You ever seen all those rainbowy holographic things? Like, stickers or cards or things that were all rainbow. That's exactly what's going on with them. They're basically reflection gratings. So the spacing of slits is the distance from one groove to the next, typically from 300 to 2,000 grooves per millimeter. And you get constructive or destructive interference because light travels different distances when reflected from each grating. And the angle at which constructive interference occurs is now given by n times the wavelength equals the distance times the sum of the sines of the two angles. That's the difference. So it's some grooved surface with a reflective coating, aluminum, gold, or platinum. It's also what this reflection grating effect is also why CDs are like that, because they have tightly spaced grooves. And the resolving power, the resolution is the order of interference times the number of grooves illuminated. Often you're actually working with a higher order of interference than just one with a reflection grating, because it turns out to be convenient. And the minimum wavelength resolution is 1 over the resulting, is the wavelength over the resulting power. So if you have a monochromator with an echelon grating of 2,500 blazes per millimeter, so let's see, delta wavelength is wavelength over resolution. Resolution is little n times number of grooves illuminated. So we have a monochromator equipped with an echelon grating of 2,500 blazes per millimeter, where 2 centimeters of the grating is illuminated. So our big N is how many grooves are illuminated. And at approximately 430 nanometers, what's the minimum wavelength difference that can in theory be completely resolved for the instrument if N equals 1? So our resolution, the minimum wavelength that can be resolved is the wavelength over the resolution. The resolution is little n, which is 1, times big N, which is the number of grooves that are illuminated. The number of grooves that are illuminated is 2,500 blazes per millimeter times 2 centimeters. 2 centimeters is 20 millimeters. So that's 2,500 times 20, which is 50,000. So R is 50,000. 430 nanometers divided by 50,000 is 0.0086 nanometers. So the general idea for a monochromator is you have some entrance slit that provides a rectangular optical image. You have a collimating lens that makes all the light beams parallel. You have your dispersive element, which is like a prism or a reflection grating, as you can see here. The collimating lens, it could be collimating lens, it could be a collimating mirror. And then you have a focusing element, which reforms the rectangular optical image focused on a focal plane. And then you have an exit slit, which selects the desired bandwidth. And then usually what wavelength you're choosing is done by rotating something like rotating the prism or moving the exit slit. Or rotating the grating or moving the exit slit. And I think generally it's rotating the grating. Just because mechanically that's pretty easy. And it lets you move it sort of side to side. Rotating the grating of the prism is mechanically pretty easy because you just need to hook it up to a motor. Rotation is easy to do mechanically. And then you don't have to worry about refocusing the light. The light is all coming out of a fixed slit. So on the other side, your optics don't have to take into account a slit that moves around. So here is an example, sturdy Turner grating. You have an entrance slit, a collimating mirror, the grating. You can change the angle of the grating, another focusing mirror, and an exit slit. And you rotate the grating to change what wavelength you're selecting. And here we have a Bunsen prism. You have a light source, a slit, a collimating lens, a prism, a focusing lens, and an imaging plane. Now, sometimes you actually do want your light dispersed like this. So I know for a lot of spectrometers on telescopes, instead of selecting individual wavelengths, they output a spectrum, and then they have like an extended light sensor, like a camera sensor, but just 1D. And that means it may not have as precise picking of wavelengths, but it grabs the whole spectrum at once, which is useful for telescopes, because with telescopes, part of the issue is you don't have a lot of light. So a grating has uniform dispersion versus wavelength. It's smaller. It has more stray light, but the wavelength and it has an unlimited range of wavelength use. Prism has a shorter wavelengths, are better separated. They're larger. Stray light is less of a problem. The wavelength range is limited by the material of the prism. An increase of size of either a prism or a grating gives you better dispersion. Stray light can be removed with filters, and glass absorbs light at less than or equal to 350 nanometers. Yeah, I'm pretty sure we have a grating in our UV setups, but I don't know exactly. And the slits in the monochromator need to be carefully made since they control the range of wavelengths emerging from the monochromator. Typical slit widths are 0.01 to 2 millimeters, and they're often adjustable. And the bandpass of the monochromator is the range of wavelengths transmitted at the half height of the transmitted light band. So there's sort of a peak that's transmitted. Halfway up, that's the bandwidth. And a typical bandpass is 20 nanometers to 0.5 nanometers for UV visible instruments. If you decrease the slit size, that decreases the bandpass, which is good, but you have less undesired wavelength, but you also have less intensity, which is bad. So it's a kind of constant trade-off. And two wavelengths can be resolved by the monochromator if they differ by 2 or more times the bandpass. So the resolution is directly related to slit size. So here we have two light rays incident on a diffraction grating, and the path length difference for these rays, and the sign convention for A and B using the grating equation. And you'll get, if you do this on a grating, you'll have order 1 and then order 0, order 1, order 2, order 3, and so on. The diffraction of light. If you have a laser and you want to estimate the wavelength, you decide to use a reflective diffraction grating to do it. The light's incident on the grating at 20 degrees with respect to the normal. The wavelength, using a grating with a groove distance of 5 micrometers, the first order diffraction is found in an angle minus 12.5 degrees, and determine the wavelength from the source. You might, so the formula is that distance over wavelength is the the wavelength is d over m. In this case, m was n in the other equation, but m here is just 1. Because it's the first order. D is the grating spacing times sine alpha plus sine beta. So 5 times 10 to the minus 6 meters over 1 times sine of 20 degrees minus plus the sine of 12.5 degrees gives you 6.28 times 10 to the minus 7 meters, or 628 nanometers. So that would be the wavelength of that light. And if you have a grating that's 25 millimeters long and it has 600 lines per millimeter, we want to calculate the distance between the grooves, the total number of grooves, the resolving power absorbing first order diffraction, and assuming a center wavelength of 550 nanometers, the minimum wavelength separation associated with this power. So the distance between grooves is just going to be 1 over the number of lines per millimeter, and then we convert from millimeters to whatever, in this case, it's to micrometers. So 1 over 600 lines per millimeter is 0.00166 millimeters, or 1.66 micrometers. The number of lines is 600 lines per millimeter times 25 millimeters, 15,000 lines. The resolving power is, if it's first order diffraction, why is that a 2? I would think it's m times n. So 2 times 50,000. I would have thought that would just be 50,000. It's 30,000. 2. I'm not sure. I might have to dig up that book because I pulled this as an example from another textbook. That's what seems odd. I would think it would be 1. And then you just divide that by resolution to get the minimum wavelength separation. Here it's one. So if you assume first order diffraction, that would be one. Yeah, that must be a mistake. I'll have to pull up the book and check after. But that's sort of the general idea. The only issue there is what M is. So other ways to get it, you can use filters. If you're interested in just one wavelength, you can have a filter for that wavelength. The advantage of that is that it's super cheap and not very complicated. So you can use a couple of filters to cut, to eliminate, to absorb undesirable wavelengths and only allow through certain wavelengths. So a material that removes undesirable wavelengths by absorbing them, they're typically made from colored glass or dye, suspended in gelatin between glass plates. They have a fixed wavelength and a lot of energy gets lost due to absorption, but they're cheap. They have a relatively wide range of wavelengths allowed through. You can combine filters with different wavelength range to get tighter filters, but you also end up absorbing more in the process. The typical bandpass is something like 30 to 250 nanometers. It's wide. Compare that to the monochromators we were talking about, where it's like 1. Interference filters use interference to create a filter that lets through only a specific wavelength. So they have basically 2 mirrors, and the gap between them is such that only certain wavelengths will constructively interfere, and others will destructively interfere. And so you've made thin layers of metal and dielectric material sandwiched between glass plates, and the metal acts as a partial mirror, and you get a narrow wavelength coming out. These are relatively inexpensive. The wavelengths transmitted through the filter are some number, n times the wavelength is 2 times the thickness of the dielectric times its index of refraction. So it's using interference to select, so it's pretty tight selection. And then it's going to be multiples of something, some value, or actually, so the wavelength times some number, whole number will equal this twice the distance between twice the thickness of the filters is corrected by the refractive index. And the bandpass can be quite narrow, 1 to 20 nanometers, but the filter is fixed at a very given value, and a lot of intensity gets lost due to the reflection. So a lot of the light gets bounced back. So let's move on to talk about sample cells. Generally, sample cells need to be transparent at the wavelength that you're interested in. So you use quartz or fused silica for UV, less than 350 nanometers, glass or plastic for visible. We actually have both. We have quartz cells, we have plastic cells. It's best if cells are flat with both match, sample, and reference cells. So you don't, the idea is to keep B the same. And many automated instruments will have flow-through cells with temperature control and other factors. We have some potential flow-through cells and things, and then we have detectors. The earliest detectors were the Mark I human eyeball or film. We now use devices that convert light into electrical signals. For a good detector, we want very high sensitivity, a good signal to noise ratio, a constant response over the wavelengths of interest. It's unfortunate if your detector responds more to certain wavelengths than others. You want the signal to be proportional to the light intensity. You want a fast response. You don't have to wait forever. And little to no signal in the absence of light, what's called dark current. So here are some example options for optics. Lithium fluoride covers a nice big range here. Materials for cells, windows, lenses, prisms. Fused silica or quartz goes through UV through into the near IR. Corax glass, silicate glass. Sodium chloride is good through UV through down into the IR. Potassium bromide is good in here. Potassium bromide, or I'm not sure what that would have been. Zinc. These are just different materials. And why you might want to choose between quartz and plastic. In the visible range, they're about the same. The gray line here is the absorbance of quartz. The black line is the absorbance of plastic. You can see in the UV, plastic suddenly starts absorbing tons of light in the UV range, while quartz only goes up a little bit. So that was the sample cells and optics, and then we have detectors. We talked about detectors. So detectors, photographic plates, were pretty good for UV visible, short UV. They're good for short wavelengths and beyond. Actually, these photographic plates continue to be good at even shorter wavelengths than shown on this graph. They stop in the near IR. Photomultiplier tubes are good through the UV visible range. Phototubes, again, UV vis and a bit of near IR. Photocells, silicon diode, similar range. Charge transfer detector, that is basically what's, if I remember correctly, that's more or less what's in your cell phone camera. Like that, it's an array of those. Then for IR, you use more, there's photoconductors, and then there's thermal detectors for heat kind of things. So thermocouples or bolometers, Golide pneumatic cells, and then pyroelectric cell capacitors. There are also some detectors if you want to go into the far IR. We'll go into a little more detail later. So a photovoltaic cell or a barrier layer cell, there's a glass with a thin layer of silver, and then selenium and iron. And the idea is that when light hits it, it knocks an electron free, which gets collected by the positively charged side, and you get a voltage. The light is sufficiently high energy, passes through a thin transparent silver layer and hits the selenium, causing electrons to be released, which move across the barrier towards the silver layer. Electropositive and are collected in an iron layer to neutralize the selenium layer. The current produced is proportional to the photons hitting the surface. The maximum response is at 550 nanometers. It's at about 10% at 350 to 750 nanometers. 350 to 700. It's about the same as the human eye. It's cheap, it's rugged, you don't need an external power source, it's good for portable instruments. Not very sensitive, it shows fatigue, decreasing response with continued elimination. It's difficult to amplify because of its small signal, because of the small resistance. A vacuum phototube has some photoemittive material. When a photon hits it, it releases an electron which gets collected in the anode. There's a potential of about 90 volts across this. And as light hits the cathode, electrons are emitted and attracted to the anode, which produces a current that is measured. The current is proportional to the number of photons. It's a smaller current than a photovoltaic cell, but can be amplified because of the larger resistance. The 90-volt difference is sufficient to collect all electrons produced. It works at saturation, and various photoemissive materials can be sensitive to different wavelengths. So different materials will have different sensitivities, as you can see in this graph. It's common to use phototubes in UV visible instruments. You have one tube for UV in most of the visible region, a second tube for the red end of the spectrum, because different materials absorb different wavelengths. Some phototubes have flat regions throughout the entire range. So the 128 gallium arsenide composite you can see here. And sometimes gas is present in the tube, and as the electrons collide with gas, more electrons and ions result in that increase in current. It's sensitive, it's easy to amplify. The disadvantage is there's some dark current from thermal emission of electrons and the natural decay of potassium-40 in glass housings. A photomultiplier tube has a light hit cathode, it emits an electron, it hits another electron, which emits more electrons. The whole process repeats until you go from like a single photon to an enormous multiplier of current. The light hits the cathode, an electron is emitted. The emitted electron is attracted to electron 1, which is 90 volts more positive, which causes several more electrons to be emitted. These electrons are attracted to data mood, which is 90 volts more positive, and so on. You need a very high voltage because the whole chain, let's say you have this chain going from with 9 diodes. That whole chain needs to the final anode requires 900 volts. And the overall voltage between the anode and the cathode is 900 volts. One photon, however, will produce something like 10 to the 6 to 10 to the 7 electrons. So this is a really good tool when you don't have a lot of photons. And so then the current is amplified and measured. It's very sensitive to low intensity and has a very fast response. The disadvantage is you need a high voltage power supply, and intense light can actually damage photomultiplier tubes. So this is what they use in things like neutrino detectors, where you're looking for a tiny event that barely produces any light. And so the neutrino detectors have some of the, so like the Cameo Candy neutrino detectors have some of the biggest photomultiplier tubes ever made. A silicon diode or a photodiode detector. There's a semiconductor material that conducts current only under certain conditions. Light shining on the silicon diode provides the energy needed for electrons to travel into the P region from the N region, and the flow of current is related to the intensity of the light. So this is sort of like the backwards version of an LED. You can actually use LEDs to detect light. But basically that's the idea, is that there's a depletion layer when you put a bias on this, and you need a little bit of extra energy to kick things up from the N region to the P region, and that allows current to flow. And the amount of current that flows is related to the intensity of the light. It's not very sensitive, but it's useful in Vidicon tubes, where you have a whole series of these. They can be used for 1 to 2 dimensional detection to detect all the wavelengths along the focal plane of an instrument. So if you have a setup that detects all the wavelengths at once, it can be useful to use silicon diodes or photodiodes. So I think, where it's an array of these silicon diodes, and the whole thing is you splay out your whole wavelength onto it, basically. And in that case, you're going to run your light through your sample first and then run it through the dispersion tool. So sometimes the dispersion tool comes first and you select a specific wavelength. Sometimes the dispersion tool comes after and you spread out your light. And you can also use like modern CCD arrays for that, which is like what your camera uses. So single and double beam instruments. So to determine the absorbance, both P0 and P needs to be measured. And there's sort of two approaches you can take to this. You can observe an empty cell. You can observe an empty cell and then observe a full cell. Or that's a single beam instrument. So this depends on the intensity of the source, the slit width, and the wavelength of the monochromator, the reflectance of the cell, and the sensitivity of the detector. So generally the process is you observe an empty cell in a single beam instrument. You measure P0 with, say, the solvent in the cell or an empty cell, if you're measuring like a liquid. And then you switch, you blank everything except the compound to be analyzed. And this is for a spectrophotometer, but you take a background. You use that to record what is zero, or what is, P0, and then you observe with the actual cell. So this is with a spectrophotometer, where this is very manual. You could adjust it to read 100% transmission or 0% absorbance. And then 0% transmission and infinite absorbance is set by blocking the light beam. And then things might drift over time, and that due to change in light source intensity, and the settings are wavelength dependent. Modern ones, it's all handled by computer. But you take a background and then you select a sample. So that's a single beam spectrometer. That's what the UV-Vis instruments that are closer to this side of the lab, the ones we have multiple ones, the smaller ones, they're single beam. So this is sort of a description for a more mechanical version of what you do. This setup is cheap and rugged. You have to readjust at every wavelength and periodically check for drift. You can have a single beam instrument that's computerized, that you take a background, then you measure the next one. A double beaming spectrometer decreases or eliminates single beam problems by basically you could instantly switch back. You have two paths. One has your sample, one has your reference, and you can basically measure them at the same time and switch back and forth. So you have a selector mirror or a beam chopper, which is like a mirror that rotates at 60 cycles per second, reflecting the light alternately to the reference or sample cells. All light gets combined and goes to a single output, and you can measure alternately this. The advantage is wavelength scanning, little drift, only one photomultiplier tube. It's more complex and expensive. So the bigger UV visible instrument that's more in the back of that lab, that can do both single or double beam. So I have trouble figuring out how to make it do double beam. Now, the IR instruments use this trick of switching from time domain to frequency domain. So here, if you have, this is two different frequencies of light. This is their power over time, and they combine to be two different frequencies. So this is a time domain plot, V1 and V2 of two different frequencies of light. The two frequencies have the same amplitude, but they're slightly out of phase. So you get a beating effect, where sometimes they're in phase and constructively interfere, and sometimes they're out of phase and destructively interfere. And this is the time domain plot you get of the interference pattern. Now, if you can record this time domain information, you can use the Fourier transform to extract the frequency information. So there's a mathematical technique that allows you to go from this to the frequency plot of these two frequencies. So the trick used in FTIR instruments is that they use interference in a moving mirror to set up time domain information. And then we can use that to extract frequency information. So using Fourier transform measurements, some advantages, the collection time is much faster because it's just the time it takes the mirror to move. So you have an interferometer set up where certain wavelengths will interfere and other wavelengths will, certain wavelengths will constructively interfere and destructively interfere depending on the position of one of the mirrors, which moves. You get a faster collection time. You have the multiplex advantage that you can take lots of measurements and average them to get better signal to noise ratio. And then you have a throughput advantage because all the light goes through. You're not cutting off a single wavelength. You're running all the light through your sample and then through this interference thing. And so you generally get better resolution. The disadvantage is you need a computer to do the math. And you need to be able to collect data fast enough to get time domain data. But yeah, so you have an interferometer with a fixed mirror, a beam splitter, and a movable mirror. So as the mirror moves for a specific wavelength, you'll get an oscillation like this. At 0, you'll have a peak. You'll get 0 amplitude at half that wavelength. The mirror is half a wavelength away. When it's at 1 wavelength, you'll get a peak again, half, peak. So this basically, as this mirror moves, which you know because you're controlling its movement, you know how it's moving. Also, you're running a laser through this to record how it's moving with a fixed wavelength. This lets you have your light source, which goes through the interferometer, goes through your sample and into the detector. Or you can either go through the interferometer first or second. I don't know exactly which order is best, but and then it feeds into the detector. I think a lot of times it goes through you have a source, it goes through the sample, and then it goes through the interferometer. I guess it depends. I guess this is implying that it generally goes through the sample. There's also a reference laser. The reference laser goes through the whole thing. The reference laser is basically used as a tool for measuring it because it's a very specific wavelength. And so how the reference laser is changing, it's generally running like literally parallel. And that feeds into the detectors, and you can use the reference laser information to get information back and to sort of calibrate. The mirror moves back and forth. And this is most commonly used with IR. But if you have enough control over the mirror and such, you can use it with visible. They exist. The good versions of the visible ones you need to, and up into UV even, you need to pump all the air out of your setup. You need to run the whole thing in a vacuum. But you can do it invisible. It's just harder because you need finer control over the mirror and faster data collection kind of thing. So it's usually used for IR because the longer wavelengths are easier to measure this way. So this is a plot of the power reaching the detector as a function of the displacement of the mirror, the retardation. You can see it's, sideways for some wavelength. And you'll have different frequencies. Each different wavelength will have a different frequency in this. And then you can use Fourier transform to convert it. And because the fast Fourier transform equation algorithm exists, you could actually do it quickly. So yeah. So you get better resolution. The microsecond interferometer resolution is greater than this, but I mean, it's technically a lot more complicated. It needs a computer. So the idea is that you have something like this corresponds to one wavelength. This corresponds to a couple wavelengths. This is something more like you actually see, and that corresponds to a distribution of wavelengths. And that's the end of chapter 7. So I'm going to end it here. We will start on infrared next week. And we should have our first lab on infrared next week, where we'll be identifying various substances. So have a nice weekend.